I passed back at the start of class. Everybody's derivatives packet that handed one in to me. So if you still have one and you need to get that turned in, please do that ASAP. I put a score at the top, but they were just graded as homework assignment, like 5 out of 5 or whatever for doing it. I just want to give you some feedback on like what the right answers were and all that jazz. Today we're going to look at, start with questions, and we're going to do section 3.7 and talk a little bit about things coming up. Sound good? Okay. Questions from stuff. Michael. Yeah, sure. Let me pull that up real quick. Okay. So this one just like, for whatever reason, when I made this, the LaTeX didn't convert, which is super annoying. So we have like 2 nonsensical answers. So let me just translate this from like LaTeX to okay. So that's what those really those 2 answers would have looked like. So if I start with my original and I do the derivative, I recognize that that's going to be 2 chain rules there, right? The outermost function is sine. So if I do the derivative of sine, that's cosine. The insides stay the same. And then I have times the derivative of the insides, right? So that's going to come down. The derivative of f is just f prime. Inside stays the same. And then I have times the derivative of that inside. And the derivative of that is 2x. So that's, and then if I want dy dx when x is equal to 3, I plug those in. So I'm going to have cosine of f of 3 squared times f prime of 3 squared times 2 times 3, or 6 f prime of 9 cosine f of 9. And I think that was answer D then. Yeah. When I wrote out what those things mean, yeah. So unless you could read LaTeX, you probably didn't know what the heck was going on there. So if you got 10 wrong, I wouldn't worry too much about it, since the correct answer was not a choice that was probably readable for most of us. Happens. I pulled them all from the AP site, so sometimes that AP site doesn't, I don't know why it glitches sometimes and doesn't convert to LaTeX. But I've seen that happen before. It's frustrating. Others with questions? Happy to do more. Elena. 30, that's the last one? Sure. All right, so we have e to the xy minus y squared equals e minus 4. And then we're saying at x equals a half and y equals 2, what is the derivative? So I'm going to start by taking the derivative of both sides. Okay, so far so good. To take the derivative of e to the xy, that is a chain rule followed by a product rule. So the derivative of e to the xy is e to the xy times the derivative of xy. The derivative of y squared is 2y dy dx. And the derivative of e minus 4 is 0. Remember, e is a constant. So that's just 0. The derivative of xy, then, if I do the product rule, is x times the derivative of y. So that's 1 dy plus y times the derivative of x. The derivative of x is just 1. So I have that. Or if I distribute things through, oops. So I have that, right? I'm now going to get the dy dx by itself. So I'm going to subtract this piece to the other side and factor the dy dx out. So far, so good. And I'll divide both sides by that parenthesis. And now if I plug in when x is 1/2 and y is 2, I'm going to get negative 2 e to the 1 over 1/2 e to the 1 minus 2 times 2. So I have that. That doesn't match any of my answers, though, so I'll multiply the top and bottom by 2 to get rid of the fraction in there. So there's that. That still doesn't match, but it's real close, right? If I look at this and I look at this one, they just differ by a negative, right? So if I multiply the top and bottom by -1, I'm going to be good to go. Does that feel okay? Paulo? Sure, of course. Addie? 29 and 28 are the same. Yup, sure looks like it, huh? That's weird. I'm going to pick 28 because it all is on one page. Makes it easier to screen cap it. Okay. So we'll start the same way. We'll just take the derivative of both sides. The derivative of 3x is 3. The derivative of tangent is secant squared. And then, since there's a y, I get a dy dx. That's going to equal 0. So I'll subtract the 3 over, getting the dy dx by itself. And then divide by negative secant y. The negatives are going to cancel. Now that doesn't match any of my answers here. What's going on? Well, it's because I know that secant is the reciprocal of cosine. So if I have secant in the denominator, it's like having cosine in the numerator. So there we go. Those trig identities. Ugh. I know, guys. Still got to remember them. The basic ones. If you remember the reciprocals, quotients, and Pythagoreans, you're golden. Michael. 14 coming up. Yes, go ahead. All right. So we have arctan of cosine x. So again, I'm just going to be taking the derivative. I notice that this is going to be a chain rule problem. The outer function is tangent inverse or arctangent. The derivative of tangent inverse is 1 over 1 plus x squared. But in this time, I'm really going to think of 1 over 1 plus inner squared times the derivative of the inside. So far, so good? Yeah, so if I have the derivative of tangent inverse of x, well, I'm going to use the letter u. That's going to be 1 over 1 plus u squared times the derivative of u. So my u in this case is cosine, so I put a cosine in there, and then I do the derivative of cosine. Is that?
So the inverse for tangent, like, when you combine with the chain rule, you just put the other part on the bottom.
So, yeah, so again, remember the chain rule is the derivative of the outside with the inside plugged in times the derivative of the inside. So like my outside here is the arctan, so I have the derivative of that, and then my inner is the cosine, so that's what got plugged in. Is that, you see it now? The trig ones are tough with the chain rules, especially when you have like one of those inside of an inverse, and like they can be kind of rough. If I finish this up, I have the derivative of cosine is negative sine, and then 1 plus, and I'll write that as cosine squared x, and looks like a. John Paul.
U21.
Yes. All right. So again, just another derivative one. Remember from last time, both the derivative of natural log of x is 1 over x, and the derivative of natural log absolute value x is also 1 over x. So the absolute value here doesn't really do anything different. I can just kind of ignore it. So I notice this is like a double chain rule, right? The outermost function is the natural log. The middle function is cosine, and the innermost function is pi over x. Or I'm going to really think about that as pi x to negative 1 when time comes. So I have the derivative of the outside. So that's 1 over the insides times the derivative of the insides. That comes down. The derivative of the inside is negative sine of the insides, and then times the derivative of that inside. And then the derivative of this is going to be negative 1 times pi x to the negative 2. So if I put this all together, let's see, negative cancels with negative. My numerator is going to be pi sine pi over x, and my denominator is going to be x squared cosine pi over x. And I notice here that sine over cosine is tangent. So I got E, it looks like. Does that feel okay? Again, like found those, like when you got those nested chain rules and the trig stuff can get tough to keep track of everything, right? But go slow and it'll be okay. Others with questions? Michael K. 16. Sure. Okay. When I look at this one, I see a product rule, then inside of that product rule is a chain rule, right? So if we do the product rule first, I'll write it out. So we have that. So the derivative of sine is 2x is a chain rule. So the derivative of sine is cosine, and then, so we have cosine 2x, and then derivative of 2x is just 2. And derivative of x squared is 2x. So if I look at this, it looks like I have, that's not one of my options, so I'm going to have to do some factoring. It looks like I have a 2 and an x in common with both pieces. So I'll factor that part to the front. And then it looks like the option I want is this one. It's not, because this one doesn't have an x. That one does. Oh. I know, that's so close, right? Yeah. Marie, I saw your hand. Yes, 3.6, number 25. All right, so this, it's a toughie. It asks for y prime and y double prime. Ooh. So if I look at 25, that's definitely a chain rule, right? In fact, I see 2 chain rules in there. So the outermost piece is the natural log, so I have 1 over the insides. And that's going to be times the derivative of the inside. Now, again, I'm going to think about that square root as 1 plus x squared to the 1/2. So I have that first piece. And then I have times 1 plus 1/2, 1 plus x squared to the negative 1/2 times the derivative of 1 plus x squared, which is just 2x. Does that look okay?
What about the natural log up front?
So when I did the derivative of the outside, that's 1 over x.
Oh, I see. Okay.
Right?
Oh, okay, I see.
Does that feel okay?
Yeah.
Now, since if I was just wanting the first derivative, I would stop here, right? But the question also asks for the second derivative, and there's no way in God's green earth I want to do that as it's currently written as my second derivative. That looks awful, right? So I'm going to do some cleanup on this first and see if I can get that into something that makes taking the second derivative massively easier. Because if I'm looking at this, I see quotient rules, I see product rules, I see chain rules, I see like a whole mess of yuck going on here that it feels like I'm going to get lost on. Do you agree?
Yeah.
Okay.
Where do you get that 2x from?
So that was when I did the derivative of this thing. So this is the derivative of the outside, and that's the derivative of the inside. Right? It was a chain rule. Do you see it now?
Yeah.
Okay.
Would
Go ahead.
you put the same inside then?
Right, I did. See the 1 plus x squared?
I was looking at the x functions.
Okay.
Gotcha.
No problem. All right, let's see what we can do to make this any nicer, because I don't want to do the second derivative of this as it's currently written. Maria, are you doing okay so far?
Yeah.
Okay. So I'm going to rewrite this stuff as a fraction. So the 1/2 and the 2 can kind of cancel. And I have x over square root 1 plus x squared. Okay there? Okay. So I'm going to make a common denominator. So that common denominator would just be the square root of 1 plus x squared. Is that okay? I'm going to multiply these two things together. So the numerator is easy. For the denominator, that stuff is going to distribute through. Does that feel okay there? Okay. Just look at that to see if... So the only thing that I don't really love is this, because that's a product rule right there. I know I'm going to have some chain rules in there. That's going to be unavoidable. I see a quotient rule. It's not going to be able to miss that. Check out this trick. If I think about that x as the square root of x squared, that's still x, right? Why would that be helpful for me to do? Because now I can distribute the x squared inside and like knock out having to do a product rule here. You like that? I like it because it seems like that's going to make my life quite a bit easier. Okay. Nate.
Could you do number?
We're not done. We still have to do the second derivative of this thing.
Okay.
I'll come back to you though. Violet?
Just like cancel out like the denominator of the first fraction and then the numerator of the second. Wait.
So, here?
Yeah, can you just do that?
Oh my gosh.
Oh, you're so smart.
Yeah, let's do that. That's a better idea than anything I just did. Great eye. Everybody see that, what she did? I just got excited to like distribute the multiplied things, and that's way better. Yeah. Way to go. All right. This, I feel like I can do the second derivative of, right? So I'm going to think about this as like 1 plus to the negative. So I have negative 1/2, 1 plus that, to the negative 3/2 times the derivative of the inside. And then boop, boop. So I have negative x over 1 plus x squared to the 3/2 or something.
Okay.
And that feels
That makes sense.
Yeah. So again, like before I dive in for that second derivative, like let's look at what I can do to clean this up and not make like an impossible amount of calculus. Right? Nate.
Could you do number 4 on the practice worksheet?
The derivatives practice? Sure. When you look at number 4, what I see is two chain rules, right? The outermost function is e to the x, the middle function is x squared, and the innermost function is tan x. So that's what you would want to see. So if I do the derivative of the outside, that's just the derivative of e to the x. And then tan squared x is really like the squared there, means the same thing. So if I do the derivative of that, that's going to be 2 tan x times the derivative of tan x. And the derivative of tangent x is secant squared. And that looks like this one. You see it now? Getting those powers on the trigs is a sneaky trick that's like actually outside of the trig function. The inside is the trig function, the outside is the exponent.
So it's e to the x, so the outside is e to the x, and then the inside is tan squared of the x. And then is there other, like, how is there other functions?
So what I have is I have like f of g of h, where f is e to the x, g is x squared, and h is tan x. So if I look at g of h of x, that's going to be tan x squared, right? And then if I do f of that, that's e to the tan squared x. So there's like 3 functions involved. There's 2 chains. Is that, you see it now? It's tough to see it initially. Like, I don't know that, in all reality in Algebra 2, I don't think you guys do enough with like decompose this composition. Like, here's the composition, like pull this apart into 2 or 3 separate functions so you get good at seeing this. I don't think you do enough really with compositions there, or pre-calculus or whatever, like in your previous course. I just don't think we do enough with this because it's a really helpful skill here to see these. Michael K.
We do number 9.
Yep. But you feel better on that, Nate? You sound so reassured. All right. So when I look at this, I see 2 chain rules, right? I see a chain rule for the natural log, and I see another chain rule with the e to the x, but they're not like linked together so much. All right, so the outermost function is the natural log, so that's going to be 1 over its insides times the derivative of its insides. Now, when I do the derivative of x, that's 1. The derivative of 4, that's 0. The derivative of e to the negative 3x is another chain rule, where the outside is e to the x and the inside is negative 3x. So that's just going to be negative 3 e to the negative 3x. I guess I'll just write it as minus. That feel okay? So I have like 1 minus e to the negative 3x over x plus 4 plus e to the negative 3x. But it actually wants f prime of 0. So when I plug 0 in, oh, watch out, Coach Fox is on his mower here, guys. All right, so I have 1 minus 1 over 4 plus 1. So that comes out to just be 0. That doesn't seem right. What did I goof up here? Oh, I forgot the 3. So I have negative 2/5. So it looks like that's answer A. Does that feel okay? I want to point out something to you guys. If this is a calculator problem, because it's a specific derivative, it's a derivative at a point, your calculator can do this. May I show you how to do it once again? We've done this before, but if you have your calculator with you and you'd like to follow along, I invite you to do so. Apparently, I have the world's tiniest calculator right now. Look at that. Like, how stupid is that looking? All right. Okay. So, what I'm going to do is I'm going to go to the y equals, and I'm going to clear out anything that's in there, and I'm just going to type the problem into y1. So natural log x plus 4 plus e to the negative 3x. Bless you. And before I get moving any further, I do want to check one thing. In calculus class, my calculator needs to be in what mode? Radians. So I want to make sure I'm in radian mode. Some of us has physics class or toggle back and forth. And all I want to do is find the derivative of that at 0, right? So if I press the math button and I scroll down to the n-derive option, so I can fill this in. So I put an x for d dx. The function I want to do is in y1. Come on, come back. So I'm going to press vars right here below the down arrow. I'll go over to y vars. I'll pick the function option, then pick y1. And I'll say at x equals 0. And I get this. What's that look like? Basically the same number as? It's like negative 2/5, right? 0.4 is negative, 0.4 is 2/5. Why isn't it exact, Mr. Kulik? Because the calculator's not actually, can't actually take the derivative and plug it in. It's doing like a fancy approximation. So it may not come out to be exact, but it's going to be darn close. What do you guys think on that? Ain't too shabby, right? Nice to know that I can do that. Yes, sir. Alex. 22. All right. So when I look at this, I see a product rule and also a chain rule, right? The product rule has to come first because I don't have like one function inside of another. I have two functions multiplied to to each other, and then one of those functions is a composition. So I'll start by writing out my chain rule. So far, so good. Oops, that's a minus. This derivative is a chain rule. So the outer function is like x cubed, and then the inner function is the x squared plus 2. And the derivative of x minus 1 is just 1 minus 0. Just write a 1 there. So far, so good. And the derivative of x squared plus 2 is 2x plus 0. So that's that. Oops. I don't know how that turned into a 3 there. So far, so good. So I have 6x times x minus 1 times x squared plus 2 squared plus x squared plus 2 to the third, right? Unfortunately, that's not any of my answers. So I have to do a little bit of cleanup here. If I look at these two, I notice that I have x squared plus 2's in common to each. So I'm going to factor out 2 x squared plus 2's, or x squared plus 2 squared. So that's going to leave in the first term 6x minus 1, and in the second term an x squared plus 2. You see that? And then I can just distribute some stuff through and combine some like terms. So I have 6x squared plus x is 7, or plus x squared is 7x, and then negative 6x plus 2. Is that any of my options? Oh, good, it is. I was hoping I didn't have to factor again. I'm like, I hate those ones where there's a leading coefficient. Does that feel all right, Alex? So the cleanup was probably the worst part on that. Oh, yeah. So like, if it was, you know, like that, then it'd be a chain rule first. You see what the difference? Okay. All right. What do you guys say? We ready to start 3-7 here? Sure. Here's the good news with 3-7. There's no new ideas. This is just about like application into some word problem stuff. Okay? So that's all we're going to look at. Okay? I have one example I want to walk through because it's pretty detailed and there's not much past that. Okay? The problems I picked out are mostly these kind of physics-y motion kind of problems. All right. So it says the position of a particle is given by the equation S equals f of t equals t cubed minus 6t squared plus 9t, where t is measured in seconds and s in meters. Find the velocity at time t. What's the relationship between position and velocity? Velocity is the first derivative of position, right? So what's the derivative of position here? Plus 9, right? Excellent. Everybody's good there? Okay. Part B says, what is the velocity after 2 seconds? What is it after 4 seconds? So I'm just plugging that in, right? But I'm not going to actually do that by hand because, well, this is a calculator or a homework problem. And I am kind of lazy. So I'm just going to go ahead and type that function into y1. And I'm just going to have the calculator do the derivative at x equals 2. So I get -3. And then at x equals 4. And I get 9. Everybody's okay? How do I know that the unit's meters per second? The velocity is always a rate of the y and x variables for our function. The y variable is meters. The x variable is seconds, so I know that my answer for the derivative is going to be in meters per second. Everybody's cool? Okay. Next it says, when is the particle at rest? What is the velocity if a particle's at rest? 0. So I just want to solve v of t equal to 0. So to solve 3t squared minus 12t plus 9 equal to 0, what do I need to do? Okay. Do you notice anything about the coefficients that might be helpful to do first? Yeah, actually, I'm going to divide both sides by 3. You could factor it out also. It does the same thing, but here I don't have the extra 3 rattling around to confuse me. Now let's factor, because boy, that's a lot nicer when there's no leading coefficient, isn't it? How does that factor? Good. So we have t equals 1 and t equals 2 as our solutions there. Everybody feel good? Okay. Next it says, when is the particle moving forward, i.e. positive direction? What is positive or moving forward going to mean? What?
Velocity value above 0.
Great. Velocity has to be greater than 0. So we'll do the same thing. 3t squared minus 12t plus 9 greater than 0. Who remembers how to solve a quadratic inequality? Well, here you can, but it's going to be easier than that because it's quadratic. Does this quadratic open up or open down? Opens up, right? So the only place where it can be less than 0 is in between the intercepts, right? So I know it's, if as long as, and I know I have x-intercepts because I solved them already. So I know it's going to be, I guess I should say strictly, between 1 and 3. Did you like that? It's a lot nicer than having to grind through any algebra if I thought about it for a minute. You guys happy so far? You get the trick that I did there to not have to do the solving? As long as it's quadratic, that's mucho niso. That's some excellent Espanol there for everybody. Draw a diagram to represent the motion of the particle. Okay. Okay. Yes, sir.
The other question I asked when it's moving in the positive direction, wouldn't that be between 1 and 3? Wouldn't that be like moving in the negative?
Oh, thank you. Yeah, we have the other way. Thank you. You're right. Absolutely. Okay. The next one asks us to draw a diagram to represent the particle's motion. So from 0 to 1, we're moving forward, right? At 1, we turn, how do I draw this again? I always forget how to do this. That wasn't going to be right.
Like below the x-axis, right?
No, I think I just want to do it like, hold on a second. Yeah, there we go. Okay. Okay, so let's do this. I don't want to. All right. So here's what we'll do. T equals 0 and S equals 0 here, right? Actually, let's do this. I'll do T equals, and we'll do 0, 1, and 3. We'll go, and then I want the position at those. When I plug 0 in for position, I get 0, right? When I plug 1 in for position, I get 4, right? And when I plug 3 in, I get 27 minus 54 plus 27. That's position 0 again. So now if I draw this thing, I start out at like position 0 at time 0. I move forward until I get to time 1, at which case I'm at position 4. Then I start moving backwards until I get to time 3 when I'm back at position 0, and then from there on I'm moving forward. Does that feel okay? So mostly I'm like graphing position. And then this is kind of like time.
So graph it based on the speed equation.
I know that the velocity equation is telling me where the function is going to turn and change directions.
Okay.
So that's why I needed the times 1 and 3, and then I needed where it was at initially to know whether it's like
Yeah, okay.
tracing backwards or forwards, kind of. Sure. But that's the general idea there. That was what I needed to do. F says, find the total distance of the particle traveled in the first 5 seconds. Oops. So here's what I can't do. I can't do just S of 5 minus S of 0. Why not? Because over the somewhere in that first 3 seconds, we changed and went backwards, right? If I wanted the displacement, then I could do that. If I want the total distance traveled, I need to do the other, right? Okay, so when am I moving forward? From 0 to 1, right? So if I do S of 1 minus S of 0, that'll be the distance on 0, 1, right? You guys agree? If I then do the distance from, we're moving backwards then from 3 to 1. So I can do that, right? Everybody's okay there? And then we're back forward again, so I can just do that, right? And I guess really I could do all of these absolute valued. That's fine. It doesn't really matter. Here's the good news, right? I know all these positions except for S of 5. This was 4. That was 0. That was 4. Oh, yeah. Oh, I'm sorry. F of 3 was 0 again. That's right. That was 4. That's 0. And then whatever S of 5 is, turns out that's 20. Everybody's okay? That I just plugged that in and just got the number. So if I do that, what do we got? 28 meters, right? Okay. And then I still got lots more. Find the acceleration at time t and the acceleration after 4 seconds. When we talk about acceleration, what do we mean? That's the second derivative of position, or the first derivative of velocity. So if I take my 3t squared minus 12t plus 9, I take the derivative of that, I get 6t minus 12. And if I want that at 4, that would be 12 meters per second, or meters per second squared. Yes?
For the one before we got 28, were you just supposed to add up the pieces?
Yep. Because I put plus signs even.
Wouldn't it be 20?
They're absolute values around them.
Oh.
Absolute values around them. Yep. I know, I snuck it in there. And then graph the position, velocity, and acceleration over those from 0 to 5. So this is what I would do. Again, I have my calculator here. So this is the position function, right? To graph velocity, I'm going to do math. I'm going to do that n derive on y1 with just x equals x. So that'll be my velocity graph. And then to get my acceleration graph, I'm going to do the same thing, except I'm going to do it on y2. I can only do the x equals x in the graphing menu. If I try to do that on the main screen, it's just going to give you gobbledygook because it's going to take whatever value is stored into your x variable and just plug that in.
Sorry, can you do like how you got 20 for like S of 5?
So I plugged 5 into the starter equation.
Yeah, but wouldn't that give you 24?
So 125
Oh, it's that.
minus 150 plus 45.
So you don't use the one that you found in A.
So it's S, not V, right? That's okay? Okay. So I got that, and we're graphing from 0 to 5, it said, so I'll change my y-axis. And here I know that this isn't, at the position is probably going to be the biggest thing. I should probably include some negatives because I know that the graph, the velocity becomes negative at one point, right? And then S of 5 was 20, so like I'll just pick 25 or something, I don't know. Go by 5s. Let's hit graph. So this is the position function happening first. Here's my velocity function drawing in. Notice it's a little bit slower coming in because the calculator's having to do the derivative to calculate the points it's using to build them. And then here comes the acceleration, which is even slower because now it's having to like do, you know, go through 2 derivative steps to get it. But, you know, it's easier to have the calculator draw the picture than me draw it by hand. You know what I mean? Art is not my forte. What do you guys think? Is that okay? You want to look at what I put in the y equals one more time? Or no? You got it? Give me something, guys. Come on. Here, nobody's answering. I'm going to show you anyway. So again, that's the starter. The derivative of the starter when x is equal to x. That's velocity. And then derivative of velocity when x equals x. That's going to be my acceleration. Right? All right. When is the particle speeding up? When is it slowing down? Okay. This is hard because what 2 things do we have to compare at the same time? You have to look at velocity and acceleration. You need to look at both of them to know whether it's speeding up or slowing down. Because if the velocity is negative, but the acceleration is negative, technically you are speeding up, right? Because you're going faster in that negative direction. You're actually speeding up. If you have a mismatch, you're slowing down. So if your velocity and acceleration sign matches, you're speeding up. If they mismatch, you're slowing down. So I know that H, is it I then? So I need T, and the values of T I need are just going to be in between. I need values in between values in between 1 and 3, right? So I'm going to pick T equals 0, 2, and 4 will be my test values. Because 1 and 3 are my ones where I change direction, right? Everybody's okay there? Okay. So I'll get my values for V of t and A of t. So I'm going to just pull these from the table. I'm going to start my table at 0. We'll go by ones. And I'll just hit second and graph. I said second and graph. Oh my God, you stupid thing. It's going to take forever to do this. Second and graph. Great. So y1 is my position. y2 is my velocity. y3 is my acceleration. So at 0, they're 9 and negative 12. At 2, we're negative 3 and then 0. And then at 4, we are 9 and 12. Oh, I goofed here a little bit. Okay. So from 0 to 1, V of t is positive and A of t is negative. So what should we say there? slowing down. From 1 to no, we have to go to 2. I messed that up. Sorry here, guys. All right. Yeah, I'll explain in a second. All right. So this is a problem, right? Because what's acceleration of 0 telling you? It's not speeding up or slowing down, right? So realistically, I have what's going on from, I need to know about from 0 to 1. I need to know from 1 to 2. And then I need to know 2 to 3. And then I need to know what's happening after 3. Those are the the zones where things can happen, right? So really, this should be 1.5. And then I should have like 2.5. And then I should have 4. Well, I know that's still negative. I know that that is now, that's negative. That's negative. That's now positive. That's positive, and that's positive. So that's what I should have done. My apologies. So here we have negative and negative. So there we're speeding up. Maybe I'll just do like one of those. And then from 2 to 3, we have velocity negative, acceleration positive though. So that's slowing down. And then from 3 on, both of them are positive, so we're speeding up. Does that make sense?
So they're both the same side. They're speeding up.
Yes. When they oppose each other, they're speeding or slowing down. Sure.
Could you pull up the graph for that?
Yeah, sure. And let's do this. Let's turn off the position function so that's just not in our way. So this is the velocity. Between 1 and 3, it's negative. And here's the acceleration graph having an x-intercept at 2. So notice here, positive and negative between 0 and 1. Between 1 and 2, they're both negative. Between 2 and 3, acceleration positive, but velocity is negative. And then after 3, they're both positive. Do you see the same thing, Violet?
Yeah.
So again, you could look at the graph to do this. I find that more often than not, putting it in a table is helpful for students, but you could certainly look at the graph and get the same information out of it. When we say positive, negative, you're just looking at above and below the x-axis, right? Everybody cool? That's the gist of the idea here for this section. So you guys, in fact, I don't think we really need to do anything but the bold problems here. Just do 2, 4, 6, 8, 10, 14, and 16. Just do the boldies. That should be fine. A couple of other rando things. I did this for you guys after looking at the derivatives practice, if you go to your My Notre Dame and you look down at the announcements, there's a link to a Quizlet I made of the derivative flashcards. So like, what's the derivative of, oh, this is the wrong side. So like the derivative of x to the n is n times x to the negative, or n to the negative 1. Or the derivative of e to the x is e to the x. Or the derivative of a to the x is a to the x times the natural log of a.
Yeah.
Okay? So again, like product rule, quotient rule, chain rule, sine, cosine, tangent, cosecant, secant, cotangent. Sine inverse, it's a derivative of sine inverse. 1 over square root 1 minus x squared. Yeah. So if you're not familiar with all these, like, time to start practicing. What about derivative log n? Or, I'm sorry, log base n of x.
1 over x ln.
Yeah, 1 over x times the natural log of n.
So on the AP,
They don't give you any of these. Nothing. Your equation sheet looks like this.
Oh, perfect.
They will absolutely give you no derivative rules, period. You'll never get one. They might give you like an area formula or something if they want you to do something with that.
This was under attached.
Yeah.
Thanks, Lucas.
There's like 6.
Hey, hold on a second. I have one more thing. One more favor to ask you guys. For the, I also teach the IBSL course. And in the course, they have to do a project. Some students, their project involves filling out a survey. I'm going to put a link also in the announcements for you guys. If you would fill out the surveys as well, that would be great.
Amen. God, thank you for the peace and restoration you have sent me today and every
This
day.
is so early.
Help me to recognize your
Still
healing
talking.
power in my life and be a source of comfort for others who are also in need of healing. And I ask this in the name of the Father, the Son, and the Holy Spirit.
All right, hold on. One more thing I want to say.
Wonderful afternoon, Notre Dame. God bless. Teacher, she made it Smith.
I am going to check with my IBSL students. If everyone in the room completes all the surveys, I will give an extra credit on the next test. Okay? So please do it. Don't forget.